Hey guys, what we're going to be talking about today is the law of conservation of energy. And then we'll be doing some example problems to see how we can use this law and what we already know about kinetic and potential energy to solve all sorts of physics problems. So right off the bat, what is the law of conservation of energy? Okay? Basically, what this says is energy cannot be created. Okay? Energy doesn't just come from anywhere. Okay? Energy cannot be created nor destroyed. Only changed. Okay? We can change the kinetic energy of our hands into thermal energy of heat. But we can't create energy. We're not creating that thermal energy out of anywhere. It's coming from the mechanical or kinetic energy of our hands, which comes from the potential energy of our food that's stored in our food, and our body breaks it down and does a whole set of chemical reactions to get that to happen. Another way of looking at this is that this is also true in a closed system. So a closed system is one in which all of the forces and everything that we're analyzing is in this one little area. There's no external forces. No external forces. Okay. We can use this process, a closed system, to be a car crash. Okay. There's only the two cars hitting each other. Those are the only forces. So we can look at that as an example of one system. We couldn't look at just the one car as an example of a closed system, though, that would follow this law, because that other car is exerting a force on it. So that's coming from outside the system. We'd have to look at the two cars in the same. So in a closed system, the total energy is constant. For our purposes, the types of energy that we're going to be looking at is kinetic energy and most of the time gravitational potential energy, though we might look at some other types of potential energy. So you can see this as the kinetic energy plus the potential energy before whatever happened equals the kinetic energy plus the potential energy after. Okay? And a little note for when we do this we can only really do in situations where we completely ignore thermal energy. We pretend friction does not exist, and air resistance and all of that. Okay? In reality, pretty much everything we do, some of our energy is lost to heat, but most of the time that is so minimal we can just ignore it in terms of all of the energy of the whole thing. So before we get into some example problems, I want to remind you of these equations. Okay? Kinetic energy is going to be equal to 1/2 the mass of the object times its velocity squared, and then potential energy of gravity, okay, is going to be equal to the mass times the gravity times the height of an object. Okay, so those are our two main equations that we're going to be using along with this concept, this law of conservation of energy. So let's look at some examples. Okay. Okay, we're going to look at two different types of examples. The first example we're going to look at is a very classic roller coaster problem. Okay, so in the roller coaster problem, we're going to start our roller coaster from the top of the loop. It's going to go down, and then there's going to be a little bump, and then it's going to go off somewhere else and do other roller coaster-like things. Okay? And I'm going to tell you guys that this height is 1,000 meters. It's a super tall roller coaster. And then this height is going to be 500 meters. Okay? So, at the top of the ramp, okay, the car isn't moving, okay? You always pause at the top of the ramp for dramatic effect. Okay, here's my car with my people in it. Don't make fun of my art skills. Okay? But at the top of the ramp, it only has potential energy. And I'm going to tell you that the potential energy of the people in this car and the cart and the whole little system right there is going to be 20,000 joules. Okay? So if the potential energy at that point is 20,000 joules and it's not moving, okay, it's pausing for dramatic effect, the kinetic energy is going to be 0. Okay, so that's at the very top of this ramp. Now what about at the bottom of the ramp? Okay, this is our height 0. At the bottom of the ramp, all of a sudden, all of that potential energy has been converted to kinetic energy, okay? It no longer has any height. So the potential energy is now 0 joules. But what's its kinetic energy? Well, we have the law of conservation of energy, which means that the total energy, the total of these two numbers, is conserved. So, if the potential energy was 20 at the top, and now it's 0, all of that potential energy was converted to kinetic energy. All 20,000 joules of it. Okay? So from the top to the bottom, they just kind of flip-flop so that the sum of them stays constant. Let's look at one more spot on the roller coaster. Let's look at right here. Now it's at a 500-meter tall ramp. Okay, so it's still going to have some potential energy because it's at a height, but it's still going to be moving too. So it has kinetic as well. You don't stop moving other than at the very top of the roller coaster ramp. So it's going to have some potential energy and some kinetic energy. Okay. I didn't tell you the mass of this cart, so we can't find it using this equation. However, I know that it's directly proportional to the height. So if it was 20,000 joules when it was 1,000 meters tall, this is half the height. Okay, 500 is half of 1,000. So the potential energy is going to be half as much. Instead of being 20,000 joules, we divide it by 2, and it is 10,000 joules. But what about the kinetic energy? Well, the total energy still has to be 20,000. So if the potential energy is 10,000 joules, the other half of it is kinetic energy. Okay? So that everywhere the total energy is 20,000 joules. It doesn't matter if you're at this point on the ramp, at this point on the ramp, at this point on the ramp, or this one, or this one, or this one, or this one, or this one. Okay? The total energy everywhere along this, if we ignore friction, is 20,000 joules. In reality, some of this energy is lost to friction, but in a well-designed roller coaster, that's pretty minimal. Okay, let's look at another example problem. Different type of example problem, a very common one though. This one I'm going to phrase as a word problem. A 60-kilogram child is sitting atop let's say it's a small slide, a 4-meter tall slide. If she slides down, how fast will she be going at the bottom? Okay. And again, we're going to ignore friction in this. It's an ice slide. She's not going to have any friction. Okay? Like a water slide. Water slides have very little friction. So, like anything we do in physics, we start off by drawing a picture. So I'm going to draw my picture. It's going to look very similar to my roller coaster picture. There is my child. Okay? And I said that it was a 4-meter tall slide. Okay? We're going to use the same principles that we used before. Don't make fun of my little child. She's sitting down here. Okay? Whatever. Okay? We know at the top she's only going to have potential energy. And down at the bottom of the slide, all of that energy is going to be converted into kinetic energy. Okay? We also know that she has a mass of 60 kilograms. Okay? So mass equals 60 kilograms. So we know her mass and we know her height. So we can find how much potential energy she has up here. Okay? So we're going to use the equation potential energy equals mass times gravity times height. Let's go ahead and plug in our numbers. Her mass was 60 kilograms. Gravity, the acceleration due to gravity, is 9.8 meters per second squared. And her height was 4.0 meters. Okay. Go ahead and plug this into your calculator and tell me what you get. Well, I get my calculator. Okay, so I got that her potential energy is 2,352 joules, or kilogram meter squared per second squared, which we can just round to joules. Okay, so we know that that is her potential energy up top. I'm ignoring sig figs, that's fine. And that's going to be equal to her kinetic energy at the bottom. We also know that kinetic energy equals 1/2 mass times velocity squared. Now we know her kinetic energy and we know her mass. We can solve for her velocity. We can solve for how fast she'll be going at the bottom. So let's go ahead and plug in some numbers. Equals 1/2 of 60 times v squared. Okay. So then I have 2,352 equals 30 times v squared, divide by 30, divide by 30. 78.4 equals v squared. Take the square root of both sides to undo the square. And I get 8.85, so I'm just going to say 8.9. Velocity is in meters per second. So that is how fast she will be going at the bottom. Seems like a pretty safe speed for the child. She'll be fine. And that's how we use the law of conservation of energy to solve problems. Okay, cool. Okay, cool.